Okay, today we're going to look at more specifically about the normal and friction forces, and there's a few different things that we got to talk about with friction, but before we get to that, I want to explain a little bit more about the normal force. So far, all we've done is we've looked at the normal as being opposite to gravity. So if we had a box just sitting flat on the ground, we have gravity pulling it straight down, and then we'd have our normal force would be the reaction force, right? Gravity is the action, gravity's pulling it downwards. The reaction force would be the floor pushing back up on the box. So it would be the opposite direction, and in this case, our normal force is equal to gravity, right? We have nothing else at play. Those two things balance out, because if it's in equilibrium, it's not moving, they have to balance out. Okay, so let's look at a different scenario where we have our box sitting on the ground. So that part's still the same. We would still have gravity going downwards. That part's still the same. But now let's suppose we're going to push down on the box. So we're going to have an applied force also going downwards. And that's it. So if we have the force of gravity and then we push down on it, that's just like having more weight on the box, so that would be like extra weight. So in this case, we're in equilibrium after we're pushing down. So our normal force in this case would be the same as the gravity plus the applied force. So the trick is your normal force is always going to balance out your vertical components. So if we have gravity going down and only gravity, our normal will be the same as gravity. If we have extra force pushing it downwards, then our normal would be gravity plus that applied force. Okay, so let's look at one more now where we have still the box on a flat ground, but in this case we have gravity pulling it downwards again. But now let's suppose this time we have, instead of pushing downwards, we're going to have a rope attached to the box and we're going to pull it upwards a little bit. So let's suppose we have a tension, we have some sort of applied force tension, and we're going to lift upwards on the box. So in this case then our normal is going to be a lot less because we're taking away some of the weight. If we're lifting up on the box, we're canceling some of the gravity. So in this case our normal force plus the tension force would equal gravity. Right, so the two upwards together will then equal all of the force going downwards. Okay, so you just got to be careful that those two, that the vertical and components always balance out. So whichever, if there's extra forces up or down, you just have to make sure to balance it out. So the questions we're going to get to today that get a little bit tricky is when things happen at an angle. So let's suppose we have our box still and we're going to push. Okay, so in this case we've got our box on the ground, but instead of pushing down, we're going to push downwards at an angle. So we're going to slide it along the ground, but we're going to be pushing downwards as well. So in this case our gravity is still the same. Our gravity would still be going straight down. And our normal force will be going upwards, but the trick in this case is we have to worry about our components. So we'd have our downward part of the force that's being applied, and then we'd also have a horizontal component going sideways. So in this case, the box will start to slide, but it's that horizontal motion that's going to slide it. So we'd have downwards force, and then our normal force then now will be upwards, and that'll balance it out. So in this case, our normal force will equal the two downwards. We'd have our gravity going downwards, plus we'd have this extra applied force. I'll just call that the force applied in the y direction. Okay, so that downwards there, and I'll only draw it in blue so we can see it's sort of the same. So we have this downwards component of our applied force plus the force of gravity. Those are both going down, so then the normal has to balance that out. That has to be the top ones. So if I wanted to color coordinate these, all of our downwards forces are blue and all of our upwards forces are red. So you can kind of see that they always balance. So For the first one, they were both exactly the same. They balanced out. For our second one, we had our normal going upwards, and we had gravity plus applied force going downwards. For our second one, it was just our gravity going downwards, and our two red ones were going up, so those two added together equal to gravity. And then our last one, once again, we got gravity and our applied going downwards. So you have to add the two downwards ones together to get your total normal force. Okay, so that's enough with the normal force. So now let's move on to friction and look to see how that works. Okay, so with friction, what we have to think about, first of all, what is friction? So after calculating, we get 49.05 for our force of gravity, so that's what we'll multiply by our coefficient of friction. And when we do that, we get an answer of 19.62. And we'll round that to, let's suppose we had 2 digits. Let's suppose the question had 5.0 kilograms. So we round it to 2 digits, it'll round off to 20 newtons. So what that means is if we tried to push this block, there's going to be 20 newtons of resistance force counteracting our efforts. Okay, so this next example, let's look at, we have a steel box, a 10 kilogram steel box sitting on top of a steel table. And from the chart, I found that the coefficient of friction for static friction is 0.74, and the coefficient of friction for kinetic is 0.57. So we got the steel box, it's stationary. The question is, if we push with 25 newtons, what will happen? So to start with, we have a force of gravity of 10 times 9.81. So that equals 98.1 newtons. So that's our normal force as well, right, if it's stationary. So we can calculate the force of friction. And in this case, we'll use the static friction because the box isn't moving. So we'd have 0.74 times 98.1, which works out to 73 newtons. So that means we're going to be pushing on this box. So let's show our 25 newtons of applied force. So we have a force applied of 25 newtons, and in this case our friction then is going to counteract that, so that's going to be 73 newtons. So the first part of the question is, if we push with 25, will it move? No. It's going to take at least 73 newtons to get this thing to move. So if I push with exactly 73 newtons, that balances out, so it's not going to move. So that means I'm going to have to apply a little bit more. So let's suppose for part B, if I apply 100 Newton force, then the question is, let's calculate the acceleration. Okay, so in this case, it's going to take 73 newtons to overcome friction. So if I push with 100, that will cause this thing to move. We know it's going to move. So the only thing that's going to be different now is we can't just go 100 applied force minus a friction of 73, because it's now, we know it's going to move for sure. So we actually have to recalculate our force of friction, because it's now going to be moving, so we want to actually use our kinetic friction number. So in this case, we'd have 0.57 times 98.1, which will make it 56 newtons approximately. So in this case then, now that we know it's moving for sure, that 100 newtons of force is going to only be resisted by 56. So our net force will be 100 plus the negative 56 for the friction, which gives us an answer of 44. So that's what our net force is. So then the question is asking what is the acceleration. So we have to go net force divided by mass. So we'll have 44 newtons divided by 10 kilogram mass originally. So that means our acceleration will be 4.4 meters per second squared. Okay, so the trick to this question is you just got to be careful if the box is moving or not. So we didn't know if it was going to move, so we had to first calculate what the static friction was, and that worked out to 73, so we had to push with more than 73 to get it to move. Once we do that, though, the friction drops to 0.57 because it's moving, so then our friction amount will be less. We have to recalculate the friction and then subtract that from the 100. So like I said before, most questions it's going to already be moving or it's going to be stopped, so we don't have to worry about the two differences, but this question is a good one to kind of show you how the different scenario works for friction. Let's do one more example. Okay, so this next example we're going to look at is we've got a box, a 49 kilogram box sitting on the ground, and we're moving this box, we're sliding this along the ground, so it already is moving, and our coefficient of friction is 0.37. So the question is, what is the acceleration of the box in this case? So you can see, I started the diagram already, so you can see we've got gravity going downwards, so we can calculate gravity. So that will be 49 times 9.81, which works out to just get my calculator going here. So 49 times 9.81 is 480.1, we'll round it off. So that's our force of gravity going downwards. So the question is, in order to figure out our friction, we have to calculate our normal force. So we've got gravity going down, but remember, because we're pushing at an angle, we're going to be pushing downwards on the box as well as sliding the box horizontally. So we need to figure out those two vectors as well. So we want to go 950 times the cosine of 20. And that works out to 892.7. And then we also want to do 950 times the sine of 20. And that works out to 324.9. Okay, so we have 324.9. I'll just clean that up a little bit. So that's our downward force along with our gravity. So you can see now in this case what we got to be careful of is our normal force then will be those two forces added together. So our normal force will be counteracting the 324 as well as the 480. So our normal force is, if we add those together, we get 805 newtons together. So we have a normal force of 805. So now the question is, how do we get the force of friction? So we can calculate that using our new formula. So it'll be 0.37 times 805, which will equal 298. Okay, so there's our calculation. So you can see now, let's kind of redraw our diagram. So you can see our upward force, our normal force, balances out our two downward forces, so we don't have to worry about that. So our net force on the box then is, we're pushing it to the right with 892, and we got friction counteracting it by 298. Okay, so we just have those two forces are applied. Horizontal force, we can call that our applied in the x direction if we want, and we've got our friction of 298. So you can see then now our net force will be those two subtracted. We have 892 plus negative 298. So that gives us a net force of 594.6 if we round it off, or 0.7. If you don't round off the decimals, we end up getting 0.6, so we'll stick with that for the time being. So that's our net force, so then we can do our acceleration question. Just divide that by the mass. So we have 594.6. Original mass was 49 kilograms. Divide those out. We get 12 meters per second squared. Okay, so you can see with this question, the friction calculation was pretty easy. The trick is we had to calculate that normal force. So the work in this question was calculating the normal. So we had to break down our vectors into our horizontal and vertical components. We added the two downward components together to figure out what the normal force was. Then we used the horizontal component with our friction calculation to solve our question. And that's all for today.